In this video, I will share with you my resources for drawing and modeling small molecules and ionic compounds. The fundamental concept in chemistry is bonding. So in order for students to comprehend why and how atoms connect to each other, it is key for them to be able to draw electron dot diagrams, sometimes referred to as Lewis structures, whether it be on paper or using digital tools like the Insert Drawing command in Google Doc or using the Canvas Chrome app, for example. So I'm going to start off by showing you the worksheet that I created to do this. Okay, so the worksheet's called Drawing Lewis Structure, and I start off with introducing the purpose and sharing my two methods for drawing. The first one is very simple. It involves determining the valence of an atom, the atom that participates in the small molecule or ionic compound. And the second method I'm referring to is the happy face model, summarized very nicely in this Paul Anderson video. And once students have become familiar with the two different methods, they can actually verify their drawings that they will be doing in this worksheet by going to a PhET simulation that allows them to build some of these molecules, certainly not the ionic compounds. Okay, but before we're ready to start drawing, I take them through a review. And the review steps to the happy face model involve the example ammonia. Ammonia, very key molecule, really helps us to create, let's start with the positive, lots of fertilizer, which we can throw on our crop. So NH3, definitely a good one for them to know. So the first thing they figure out is what's the electronegativity difference between the nitrogen and the hydrogen atoms. And because that electronegativity difference is actually less than, not greater than 1.6, they will actually skip this step and proceed to actually draw their ammonia molecule. Now I can show you that in the key. So we're going to scroll down a little bit. Again, the electronegativity difference is 0.8. So as we scroll down, you can actually see how that happy face model is explained here. And then we have an actual stolen picture from the internet to show you the actual electron dot structure. But sometimes we are coming across small substances that have an electronegativity difference that's greater than that roughly 1.6 cutoff. That would be the case for sodium chloride, table salt, pretty important substance, and calcium chloride, another ionic compound. Now, the valence electrons are obviously not shared, as in covalent bonds, but again, they are transferred. So we would draw that slightly differently by showing you the positive and negative charges of the respective ions, as shown in these electron dot structures here. So once now we've gone through those review steps, let's go back to the non-key version. We're going to scroll down, and I've delineated here some directions for the students that help them what they are going to put down for the different steps for each of these small molecules that I've chosen them to draw, and also a couple of ionic compounds that I've included. And so since these directions are pretty clearly laid out, I will not go through them step by step, but I'm going to leave that up to you if you'd like. But let's at least go through one of them. So let's pick an interesting molecule. We could pick hydrogen, just 2 atoms, very basic. Don't want to do that one. We could pick oxygen, pretty important one since I'm breathing it in right now. Don't want to do that one either. I feel more like doing water, H2O. So we know the name, we can determine the electronegativity. Hopefully, again, I'm teaching in New York State. They would use the New York State ChemRef table, and they can figure out that it's less than 1.6, further confirming that H2O, being all nonmetals, is clearly a molecule. So they would highlight the molecular word, cross out the ionic, and they would then also determine that these are polar covalent bonds. And then because there's a lack of symmetry in both the X and Y orientation, water is a dipole. It has a dipole and is thus a polar molecule. Thank goodness. They can then also indicate which atom, in this case oxygen, is the delta negative, the partial negative charge. Oxygen because it pulls harder on those valence electrons versus hydrogen. The hydrogen's pulling less hard and they have a more delta positive partial charge. The number of bonds is obviously 2, but let's go and draw it. So we're going to draw it here using canvas. Now, of course, I've already drawn it in this particular example right here, but let's start anew to show you basically from fresh, okay? Sure, we could pick black, but for the heck of it, let's pick red, choose the pen, and I'm actually left-handed. I'm using the mouse here with my right hand, so bear with me. It's going to be a little crooked. I can do it. So here is the oxygen. Looks a little bit opaque, but let's go with it. And let's put the actual dots representing the valence electrons around it. From my memory, oxygen, group 16, 6 valence electrons. Let's put 6 dots around them. So north, south, east, west. We've got 2 more to go. I'll put one here, a nice lone pair. I'll put another one here, nice lone pair. Now let's bring in the 2 hydrogens. All right, hydrogen, I don't know, let's give it a color blue. So I'll put 1 hydrogen down here. That's a pretty fat H. We'll throw in another pretty fat H. And each hydrogen has only 1 valence electron. Let's dump it in. 1 here, 1 there. That's pretty good. Okay. Because these bonds are clearly polar covalent, let's throw in some deltas, partial charges. I'll do the one for oxygen since it's pulling in harder. We're going to put a delta negative here. Ooh, that's a nice delta. And then for the hydrogen, since I want to stay color coordinated, we're going to put in a couple of delta positives down here, showing you the clear polarity of this molecule. All right. Let's dump this gorgeous drawing into the actual document. So I use Snip as my tool. This shows you the previous drawing that I'd already created, but hey, I want to show off my new drawing. So we'll take that and minimize it and dump it right here in the insert your drawing. Bloop. So I think that the Canvas app did that very well. Let's verify that drawing. So we're now going to travel 1, 2, 3 to the PhET simulation. I could choose single, I could choose multiple. Let's choose the playground because, you know, it sounds like it's more playful. So let's enter that playground, and since I'm simply, oh, look at that. I had already built it, but okay, for good measure, we could hit the reset button behind my head. You didn't quite see that there. We'll build it again. So oxygen in the middle, we got 1 hydrogen on the left, another hydrogen on the right. We'll click the 3D structure. Woo, that was big. And this allows you to actually move it. If I now click on the right little image, it actually shows you the bonds, 2 polar covalent bonds. And now I'm posing my students with a thinking question. Thinking questions are important. Let's see what that thinking question is. Thinking question: why is this substance bent in terms of its shape? Tough one. So if we look at our actual drawing, is it still big in Canvas? Yeah, it's still pretty big. We see these 2 lone pairs, and those lone pairs are of course made of 2 sets of valence electrons. Electrons have a negative charge, so the students could maybe think, okay, negative repels negative. So that might mean, that might present them with the reason as to why these 2 bonds are pushed down, and that could be an explanation as why water assumes a more bent structure. Okay, so what else do I have in this assignment? So I had them draw hydrogen, I had them draw oxygen. Water seemed like a pretty important one. Let's take a look at some of the other molecules I'm having them draw. Well, considering that our atmosphere is 80% nitrogen, I figured that was a pretty important one too. We breathe out carbon dioxide as a result of us doing cellular respiration. Pretty good one too. Plus, we're spewing a whole bunch of that as a result of our current climate change issue with the burning of all our fossil fuels. Magnesium chloride, besides table salt, is a key ingredient in road salt, considering we're in New York State and we're in the midst of a winter, though not a very cold one, I should say. I figured that was an important one to draw. Again, because this molecule is an ionic compound, so I should say not molecule, but ionic compound, you cannot verify that drawing in PhET. PhET only allows you to do the molecules. The other one I chose is methane, itself another greenhouse gas. And I also chose formaldehyde, methanol, as another one for them to draw, hydrogen sulfide, and then lastly, and pretty importantly, because it's pretty much in everybody's kitchen, and that is sodium bicarbonate, baking soda. Because that one's pretty tough because it involves not just the monatomic ion sodium, but also the polyatomic ion bicarbonate. I actually linked here a YouTube video in my handout to help them draw that bicarbonate ion, which is a little bit more difficult. And so how I end this worksheet is I basically present them with an extension. So what does the extension allow my students to do? Well, they can pick 2. You could choose whatever you want. You could have them pick 3, or you can make them do it for all of them, but let's keep it simple. Pick 2 of those favorite 10 substances and kind of do an internet search. Check out what their key, main physical and chemical features might be and their common uses. And can you then make a relationship between possibly the polarity of the given substance and some of those physical features? And why are those chosen substances actually relevant? Why did I put them on this worksheet? Why are they important to know? And then they're going to summarize all their findings below. Okay, so that kind of summarizes what I do to teach my students how to draw Lewis structures, how to let them play with the simulation of building it online using the PhET program. Don't forget that I also have a video out on how I review bonding, which follows the electron dot diagrams. And I also have another video that helps my students to actually take notes on, say, again, the concepts of bonding using an app called Google Keep. So again, both of those videos are linked up above. And thank you so much for watching. See you in my next video. Bedankt voor het kijken en tot ziens.